Hey guys, and welcome back to another A-level maths tuition video. Today we're going to be covering differentiation and differentiation from first principles. So first of all, what is differentiation? Well, it's a way of getting a function to tell you the gradient at any value of x. You might think, well, why do I need this, right? Well, the normal way of finding, well, the original way of finding the gradient of a function is if it's a straight line, all you do is you find the difference of 2 points, right? And it works perfectly fine. However, most functions are not straight lines, right? Instead, we tend to have things like exponentials, or we could have a kind of a cubic graph or a quartic graph, so most graphs are all wiggly. Now if I want to find the gradient here, I can use maybe the difference, this kind of method here. But if I want to find, let's say on this curved part, I have to draw a tangent and then find the gradient of the tangent. And then what if I wanted to change it and find this one? Well, then again I have to draw a tangent. And the problem with this is, one, drawing the tangents is always an estimate, because you can always angle it slightly differently. And two, it's tedious, right? If I want to move slightly over to the right, then all of a sudden I need to redraw a whole nother tangent. So this is not a good method for us to use. So instead, it's very helpful to use differentiation as opposed to that. And that will create a function that will tell us what the gradient is at any point. Or if the gradient's constant, it will just give us a number. So the question is, how do we get this? Well, it actually uses, mathematically speaking, it uses the same principle as drawing a tangent. However, the tangent is A, going to be perfect because it's done mathematically rather than graphically, and B, we make it vanishingly small. So we get an equation for what the gradient will look like at any given point. So that's all well and good, so we need to discuss how we're going to do this. Well, the first thing we're going to do is we're going to work it out from first principles. So this is essentially, how do we do this mathematically from scratch? Okay. Now I will like to preface this. Differentiation comes back in A2 maths and it's a lot more complicated. There's a lot more functions that we differentiate, so sine, cos and tan, exponentials, logarithms, etc. And the thing is, we don't have to do it from first principles. We have predefined results. Okay, so for example, the differentiation of sine x will always give you cos x. Okay, you don't have to prove it, but for the sake of this, so you can see what's happening with differentiation, we need to be able to do first principles. And there are questions that literally say, show that the differentiation of this function is this from first principles. So we need to know how to do it. But again, when we're just normally differentiating, we don't need to prove it this way. So what we do is we will have some kind of function, f of x, and to differentiate, we normally just put a little apostrophe. That means it's the differentiated version. And the way we take this, and you're not going to have seen this before, but I promise you it's not that bad. Now those of you that are actually interested in maths and doing maths at kind of university or physics and things like this might look a bit exciting to you, slightly. But essentially what we're going to do is we're going to take our function and add h, okay? Then we're going to subtract the original function, divide it by h, and then see what happens when we reduce h to 0. We're not going to make it 0, we're going to gradually reduce it and see how the function behaves. And that is how you find differentials, okay? So that might seem a bit far-fetched, but if I give you some examples, I can show you how it's done, okay? So prove from first principles that the derivative of f of 4x is 4. So what we're going to do is use our little formula up above. Okay, so our function that we're trying to differentiate, and again, when you differentiate, you find the derivative. Okay, so the derivative of 4x is 4, means if I differentiate 4x, I should get the number 4. Okay, so if I do this, f of x is equal to 4x. Now, f of x plus 4, I'm replacing x with x plus 4, so that would be 4x plus 4. Okay? h, sorry. Now if I look at this formula here, let's substitute it in, shall we? So, f prime x, so the first derivative is limit as h tends to 0 of f of x plus h, which is 4 x plus h, minus the original function, which was 4x, over h. So again, we don't do this now, because obviously as h tends to 0, it looks like the function's going to go off to infinity because we're dividing by something that's approaching 0. But let's actually have a look at what happens. So, we expand the top, as usual. So we have 4x plus 4h minus 4x over h. Okay. Then all we need to do is simplify this. So 4x minus x is going to give me 0, and then we have 4h over h. Okay. Which again will just equal 4. And again, this is for the limit of h tends to 0. Okay? So again, this thing looks a bit fancy, but for the purposes of AS maths, it's not really that bad. Okay? All it's imagining is, imagine if h is 0. So if I imagine h is 0 in this case, can you see that that would just give me 4? Because there is no h. So h is just going to equal 0, so it's just going to equal 4. So we've proved from first principles that the derivative of 4x is 4. Does anyone have any questions about that? So again, it is a bit obscure, and the next one that we're doing is actually going to be a bit harder. It's a bit more complicated. But hopefully that's okay. Perfect. So, proof from first principles that the derivative of x cubed is 3x squared. So again, let's define what our function is. We're trying to differentiate x cubed. So f of x plus h, again all we do is we replace x with x plus h, so we have x plus h cubed. Then our derivative is the limit. Again, I'm going to be a bit lazy, and hopefully I'm not going to write limit every single time until I actually take the limit. And we have f of x plus h, so we have x plus h cubed. Again, I'm just using the formula here. Minus f of x, so minus x cubed over h. Okay. So if we write what that equals to, we have to now expand the brackets, unfortunately. So if we expand the first two brackets, we're going to have x squared, right, plus 2hx plus h squared, and that's still going to be multiplied by x plus h minus x cubed. So now we have x cubed plus 2hx squared plus h squared x plus hx squared plus 2h squared x plus h cubed minus x cubed over h. So we have a lot here. So what we're going to do is nice and quickly cancel this down. So x cubed cancels with the x cubed. Now how much 2hx squared do we have? Well, we have 2hx squared. We also have another hx squared. So that gives me 3hx squared. So that covers that and that. Then we have 3h squared x. And then lastly, h cubed over h. Now what I'm going to do is just divide through by h. So cancel, 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 cancel. So I'm left with the limit as h tends to 0 of 3x squared plus 3hx plus h squared. Okay. So, if we have a think about that, if h is becoming 0, these two terms will go to 0, right? As I make h smaller, those terms get smaller and smaller and smaller and smaller and smaller. So the only thing I have left is 3x squared. So again, f prime of x will just be 3x squared. So again, proof from first principles that the derivative of 2x cubed is 6x squared. So we have f of x equals 2x cubed. So then f of x plus h will be 2x plus h all cubed. So again, if we substitute into our formula, that means f prime of x equals the limit, as h tends to nothing, of f of x plus h, so 2x plus h cubed, minus the original 2x cubed over h. We can kind of cheat because we just did x plus h cubed, right? But let's be a bit authentic and let's actually do it again. So we have 2x squared plus 2hx plus h squared times x plus h minus 2x cubed over h. So that means we have 2x cubed plus 2hx squared plus h squared x plus hx squared plus 2h squared x plus h cubed minus 2x cubed over h. Again, we're going to gather the like terms. We have x cubed. We have, so we can cancel that one out. We have 2hx squared and hx squared, so that would be plus 3h. Then we have 3h squared x, so we can get rid of those two. And then h cubed minus h. Then we can finally expand the brackets, and we have, so we can actually cancel out the 2x cubed and the 2x cubed here. So that leaves us with 6hx squared plus 6h squared x plus 2h cubed over h, which we can now cancel a h from everything, and we're left with the limit. Again, I am being a bit lazy and not writing limit every single time, but that would make me want to kill myself. Plus hx plus 2h squared. And once again, if we have a look, if I make this h approach 0, then these two terms are going to disappear, which leaves me with 6x squared, which again is what the answer is. So today we'll be doing all of the differentiation from first principles. We'll do proper differentiation next week. Those questions can be a bit tricky, but again, this is just to show you what you need to do. And again, please keep in mind that in A2 there are some first principle proofs that are a bit trickier with like sine and cos for some exam boards, so getting really good at this is pretty damn vital, even though it may seem very tedious for you at the moment. Squared, which means f of x plus h will be 5x plus h squared. So prove that it's 10h. So once again, f prime x is the limit of h tends to 0 of f of x plus h, so we have 5x plus h squared minus 5x squared over h. So again, we can start pumping this out. So that gives me 5x squared plus 2hx plus h squared minus 5x squared h. Once again, this 5x squared is going to cancel with this 5x squared, so we're just left with 5 times 2hx will be 10hx plus 5h squared over h, which means we can cancel out h from everything. And again, you should find that in almost all cases, the h is going to cancel, which should hopefully make sense, because what would happen if this h on the bottom doesn't cancel? Well, depending on how well versed you are with maths, to just an A-level brain, when h tends to 0, it means our fraction's going to approach infinity, because we're dividing by a number that's smaller and smaller and smaller. Again, for those of you that may know a bit more maths, there are some other weird things that can happen, but in this case, we just have f prime of x is going to now equal to the limit as h tends to 0 of 10x plus 5h. So again, if you have a look at if I imagine that this is becoming 0, this term here is going to get smaller and smaller and smaller, while this term isn't going to change at all. Which means, as h approaches 0, we can say that this thing goes away, so that means f prime of x is simply equal to 10x, which once again is what they've asked me to show. This will be the last question we do today. Again, this was a fairly short lesson, but it's not too bad. We're going to do the proper differentiation next week. Gets a bit more tricky, gets a bit more fun. Proof from first principles that the derivative of kx cubed is 3kx squared. And we'll actually finish this video off with me kind of showing you what the shorter way to do it is. Okay, but again, you do need to know first principles, I'm afraid. So, we have f of x is kx cubed. And we also have f of x plus h is kx plus h cubed. So once again, zero of kx plus h cubed minus kx over h. So that equals, once again, we're going to have to do this fun business. We have x squared plus 2hx plus h squared, and there's still an x plus h on the end of that, minus kx cubed. And we can start expanding the brackets. Again, we have x cubed plus 2hx squared plus h squared x plus hx squared. So just for those of you who know, I'm doing the timesing everything by x first, then timesing everything by h. Close the brackets. And all of that's over h. So we have k, and now we can actually start simplifying. So we have x cubed, that's fine. So we can cross that one off. 2hx squared plus hx squared, so we get 3hx squared. Yep. Confusing myself now. And then we have plus 3h squared x. And then lastly, plus h cubed minus x. And then again, all over h. And equals, cool. So again, we can cancel that kx cubed with that kx cubed. We're going to have 3khx squared plus 3kh squared x plus kh cubed all over h. And once again, we're going to cancel out h from everything. And we're left with, finally, as h tends to 0, 3kx squared plus 3kh plus kh squared. And once again, if I take the limit as this tends to 0, these last two terms will go to 0 because we're timesing by a smaller and smaller number. So all we will have when we have f prime of x is simply 3kx squared, as we've done before. So this video was a lot shorter. A few reasons for that is that this is a fairly short topic, but it's long enough that I don't really want to do the other differentiation with it. So when people look up the lesson on YouTube or whatever, they will be able to find differentiation from first principles and then also just plain old differentiation, because the differentiation questions can get a lot more tricky. So you have like 6 markers and 7 markers. Again, that's AS differentiation. A2 differentiation goes even further. So that's where we'll leave it for now, and I hope to see you in the next one.